Are you looking to create your own Eurorack modules but find some of the electronics concepts intimidating? This video series may be just for you. In it, I'll cover a module that has some of the most basic electronics you'll find, the mixer. I'm Brian from Eurorack DIY, and I'm here to share with you how I make inexpensive Eurorack modules that sound and look great. Welcome back to Eurorack DIY. In my last video series, I left off my demonstration of the multiple I designed by distributing a volt per octave control signal to two different oscillators. With a patch like that, we have the start of a way to make some more interesting sounds, like maybe do something like tune both oscillators a fifth apart to play a chord sequence. But we still need to combine those sounds back together. That's where mixers come in. Mixers in Eurorack systems can vary quite a bit in size and complexity, and even the types of capabilities they have. Everything from a simple 2 or 3 channel audio mixer that only combines a few mono inputs into a mono output, to more versatile mixers with a small number of channels that can mix control voltages to be able to add, invert, attenuate, or do a combination of all three. I'm going to stick to the basics in this series and create a simple, small audio mixer and demonstrate the basic circuit concepts that make it work. Perhaps in future videos, I'll take a look at some of the features that go into those more versatile mixers. Voltages in any electrical system are measured as a difference in potential and usually referenced to one electrically connected point, most often referred to as ground. This is a common symbol for a battery in a schematic. If you look closely at a battery, you'll see one of the terminals is marked with a plus sign and one is marked with a negative sign. This means that the plus sign has a positive voltage as reference to the minus sign. It is often assumed that the terminal with the minus sign is also the reference voltage or ground. Schematics will often leave out the battery or the power supply entirely, and as a shorthand show where the circuit is connected to a supply voltage, either like the positive side or the negative supply voltage or to the ground reference. You might see that also like this example of an op amp where the plus 9 volt supply voltage is connected to one side, the minus 9 volt to the other, one of the pins on it is connected to ground. The patch cables used in a Eurorack system have the ground reference on the ring of the connector, and the tip carries the voltage signal as it alternates between a positive and negative voltage typically. This becomes important as we build our modules and lay out their circuit boards, where we need to make sure that we get the jacks connected to the rest of the circuit correctly, specifically the ground or reference voltage. The audio signals are distributed around as an alternating voltage, typically being 10 volts peak to peak, which means that they go from a positive 5 volts to a negative 5 volts as referenced to a ground. And this changes over time. So we'll see the signal going back and forth over time. We can also use two batteries to create both a positive and negative voltage relative to ground. Going back to this example, if we draw in a second battery, also 9 volts, and hook its positive side to the negative side of the other battery, we'll go ahead and we'll call this ground, and the negative side will be our reference or our negative voltage. That way, if we measure the voltage between this terminal and ground, we'll still see the same 9 volts that we saw before. But if we measure from this terminal to ground, we'll see a minus 9 volts instead. A mixer adds 2 or more different audio signals together and makes them available on its output jack. Depending on the nature of the signals being added together, it can become possible to have voltages that exceed the supply voltages of the module and certainly more than the accepted 10 volts peak to peak. For this reason, mixers often have a potentiometer, a variable resistor, to control each of the inputs in the module. These are the knobs on the module. So what does it take to add 2 voltages together? Let's take a look at one of the easier to understand electrical components we have, a battery. In this case, 2 9-volt batteries. A battery usually has a positive and negative terminal marked with a plus and minus sign respectively. We'll assume for this description that the negative terminal is our reference or the same as ground in our module. This could be confusing because modules also have a negative 12 volt supply, but that's reference to the ground signal on the power connector, which is also connected to the jack's sleeve contact. We can measure the battery's voltage with a multimeter. To do this, we'll connect the negative terminal, usually the black wire, to the common input of the multimeter, and the positive voltage to the red wire, which also goes to the voltage input. As you can see, we get about 9.7 volts, which is a little bit higher than the 9 volts that the battery says it is, and this voltage will actually depend on the battery's charge and a number of other factors. So is it possible to simply wire the two reference points, the negative terminals, together, and then the two positive terminals, and be able to see the voltages added together? Let's go ahead and try adding these together on our breadboard. First, some breadboard basics. The holes here you can plug components or the leads from components into, and you need to know how they're connected together. Along the long ends of them, these buses marked with the black and the red, plus and minus, these are all connected together in one long row, each of these two separately, and then likewise on the top here. And then on the in the rest of the breadboard, each of these 5 connections here, like these 5 and then these 5, are connected together, separate from each other. So you can do things like plug integrated circuits in across the gap in the center, and then you have multiple other connections that are available to plug things together. I've provided links below to some of the equipment that you can use to start building up your own DIY lab, and there's some things that are pretty inexpensive, like this voltmeter is just a little over $10. The busboard itself is a little bit more expensive. You can get cheaper versions. I prefer these because they're more reliable, and would recommend that for the time you spend working on circuits and stuff and all the other things that can go wrong, it's probably a good idea to get this. But anyway, to try and add these together, we can first of all hook both of the ground pins, the reference voltage of 0 volts, together on the negative bus. And then if we go ahead and do likewise with the positive pins, or the 9-volt pins, wires, we can see that we still only get 9.7 volts out of the two. So as we saw, you can't simply connect two wires containing a voltage or signal together if their voltage is referenced to the same point or ground and get the addition of those two voltages. That actually makes sense because this is a classic beginning circuit to analyze. Two voltage sources connected in parallel. In such a circuit, the two batteries don't create a higher voltage, but are able to supply twice the power to the circuit. Sometimes beginner electronics tutorials try to explain concepts by avoiding math. While the math in electronics can be intimidating, it's not always that hard, and understanding how it applies in our circuits can be important to debugging our circuits when things aren't working as intended. So I'm going to be covering a little bit of electronics math, but only enough to understand why our circuit is able to add two signals. The first bit of math we'll talk about is Ohm's law. It is used to determine how voltages and currents are related to each other given the resistance of a circuit. If we go back and look at the difference in voltage potential that we talked about earlier, 9 volts here, and we complete the circuit by putting a resistor into it here, we will have current that flows around the circuit in this direction. In this particular instance, the circuit's being represented again by the battery symbol that we talked about. This is a resistor symbol. The jagged line is the American representation of it. This resistor is 1,000 ohms, and the ohm symbol being the omega symbol. And then this is the equivalent circuit here using a voltage source and ground and showing the resistor as 1K. It's also the international, the IEC symbol for resistance, the 1K being the same value. Current flows downwards through it the same way. K represents thousands, units of thousands, so 1K means 1,000 ohms. Ohm's law itself is defined as V, the voltage of the circuit, is equal to I, the current, which is measured in amperes, times R, the resistance, measured in ohms, as we said earlier. Now, this is one form of the equation, and it's useful for solving for voltage if you know the current and resistance in the circuit, but there are other instances as we analyze circuits and look at them and think about them and talk about them that we'll want to know. So for instance, if we wanted to know what is the current in a circuit, if we were given resistance and voltage, we would solve this equation for current, or for I, and to do so we would divide both sides by the resistance, R, In this case, it cancels. The two R's cancel on the right-hand side. And if we rearrange this, we will get I, the current in amperes, is equal to V divided by R, voltage divided by resistance, or ohms, in ohms. This is useful for figuring out the current in your circuits, because it's difficult to measure current in a circuit without having to break the circuit and insert your measurement devices into the circuit to be able to actually measure the current going through it. And so oftentimes we need to be able to figure out the voltage or the current going through a particular portion of the circuit by observing the voltage and resistance somewhere, and the voltage drop across the resistance that we know about. Likewise, we can solve for the resistance of a circuit, and we do this by dividing both sides of the equation by the current, I. In this case, the two I's cancel on the right-hand side again, and then simplifying the circuit, moving the R over to the left-hand side, we see that resistance is equal to the voltage, or voltage over the current. And this can be useful for certain kinds of things too, as we design circuits and things like that. One of the most common situations is if you have to pick a dropping resistor for an LED in a circuit. The LED will need to have a particular voltage and a particular current going through it, and you'll need to solve this voltage over the current. You want to drop a certain amount of voltage across the resistor to get the right current through it, and so you can use this particular equation in that particular case. Now, going back over to our circuits that we've drawn here, the two equivalent circuits, we want to solve for the current flowing through the resistor in this particular case. So we'll go back to our current equation. I is equal to V over R, and then we can substitute in the values that we know that we have. So in this case, we know that the voltage is 9 volts, and it's divided by a resistance of 1,000 ohms. Solving for the equation, we get 0.009 amperes again, or amps, typically said, for the current flowing through that portion of the circuit. And then oftentimes we'll simplify this to get rid of the leading zeros and use units of milliamps. And so in this case, this is also equal to 9 milliamps, or they would do 9 MA. And then a small m denoting thousandths of units. Falstad's Circuit.js is a great online tool for simple circuit simulation. It provides some nice visualizations of how the current flows in a circuit and various options to observe the state of the circuit throughout. And while it's not as sophisticated as some simulators like SPICE programs or another online tool that I like, Circuit Lab, it has proven to be sufficient for me as I've worked out various synthesizer-related circuits. I'll leave Circuit.js links to all the circuits I describe in this video below, and I'll also leave a link to Circuit Lab if you'd like to try something out that's a little more sophisticated, but that also costs a bit. So let's go ahead and look at the circuit for our battery and resistor example in Falstad Circuit.js. It seems like every schematic capture tool is a bit different, with different commands to use and keyboard shortcuts and the like. It's good to learn the shortcuts for the tools you use most. For this tool, you can place any component by selecting it in the menu, then dragging it to where you want it to be. So for instance, to create my voltage source, or the battery, I'll go to Inputs and Sources and add a voltage source, a two-terminal one, and not the AC one. If we drag up, we'll get the battery in the correct polarity for the way we've drawn the circuit so far. I'll hit Escape to get out of the drawing mode to draw those batteries, and if I double-click on it, I can set the parameters for it. In this particular case, we want it to be 9 volts because that's what we were using in our examples. Also, you can use keyboard shortcuts. So in this particular case, to get the resistor, I can just type the R key. It puts me in the mode to draw a resistor, and likewise, I can just draw the resistor by clicking and dragging down to get it. Conveniently, the resistor, the default value you get for a resistor is the 1K ohm that we used in the example, so I can just leave that alone. I'll right-click again now, and what I want to do is I want to add an output, in this case an ammeter, and I'll hook that into the circuit so that we can see the current flowing through the resistor. Now we have everything that we've talked about when we looked at how to analyze this circuit with Ohm's law, and all we have to do is wire everything up. Again, the keyboard shortcut for getting into wiring mode is W, so I'll hit the W key, and then just click and drag from each of the nodes to draw everything in. This particular tool, we could go ahead and connect like this, but to keep everything nice and neat looking in our circuits, we're going to go ahead and then draw it together like this. And with that all done, we now have current flowing through our circuit, and we can see that the ammeter, which doesn't change the circuit in any way, it simply measures the current going through, gives us the 9 milliamps that we saw in the analysis that we did earlier. We can also demonstrate this with a 9-volt battery and a 1K resistor and measure the current using our multimeter. First of all, just to show you, this is a 1K resistor. We have our multimeter set on the 20K range, and it's reading 0.97K, or almost 1K ohm for the resistor. Let's take a quick look at the circuit that we have set up here. It has the battery hooked up. The plus 9 volts is on this red rail up here. The negative we've gone ahead and hooked to the bottom row. We've gone ahead and put the resistor in a circuit by hooking the 9 volts to it, through the 1K ohm resistor to the other side, and now we've left a gap here where we're going to measure the current through this. This is the part where I talked about earlier that you have to measure currents by actually changing the circuit and being able to put your multimeter into the middle of the circuit. So we know that this is going to measure in milliamps because of what we've calculated and shown already, so we'll put the multimeter on the appropriate range, in this case 20 milliamps. It's important to make sure too that when you're measuring currents and stuff that you have your leads plugged in the correct places, because sometimes for the higher current ranges they'll have them somewhere else on the multimeter. In this particular case we're measuring low current, and so it's in this one. Also though, pay attention to the fuse settings and have a little bit of an idea how much current you're expecting to see, otherwise you'll burn fuses out and have to replace those on your multimeters. So then all that's left to do after we have the circuit is go ahead and connect our multimeter into the circuit. Nothing's going through it now because we do have this gap, but as soon as we hook this up, it will complete the circuit, and then we'll see that it's measuring 9.6 milliamps, just as we expected. Now that we have a sense for how current flows in the simplest of circuits, let's talk about what happens in a slightly more complex case, like where the circuit splits apart and flows in multiple directions. In this case, we'll use Kirchhoff's current law to complete our analysis. We'll start off with the same circuit that we were looking at before, or similar to it, with the 9-volt battery and then the 1K ohm resistor. In this case, we knew that 9 milliamps was flowing down through this direction. We'll also add a 2K ohm resistor, and so this is where we get the branch in our circuit, both up here and both down here. What we're going to look to solve with Kirchhoff's current law is what is the current flowing out of the battery and thus into this particular node here, given the resistors that we have in the circuit. And of course, representing the schematic in a slightly different format, but the same exact circuit down here below. So what Kirchhoff's current law states is that the sum of currents going into a node, and there can be, in this case we have 3 exactly, but you can have up to n, as many circuit currents as would actually flow into the node. But the sum of all those currents is equal to 0, meaning that everything that's flowing into the node eventually flows out of the node, in terms of some of these will be positive into the node and some will be negative. So the first thing we need to do to complete the analysis for our equation is to figure out what the current flowing through the 2K ohm resistor is. And going back to Ohm's law, what we know is that the current is equal to the voltage divided by the resistance. In this particular case, the voltage is still 9 volts across this 2K ohm resistor. It has the same voltage potential as that. And then what's going to be different here, though, is that it's now a 2000 ohm resistor. And so in this case, the current flowing through the 2000 ohm resistor will be exactly half that of what's going through the 1K ohm resistor, or 4.5 milliamps. So now that we know that, we can go and draw up the Kirchhoff's current law equivalent of what's going on in this particular node here, with these being the currents, and then we'll choose these directions for them. And so we'll have this be I1, this can be I2, and this will be I3. And so what we know is that I1 plus I2 plus I3 will be equal to 0 amps, milliamps, whatever we have. And then we know that I1 is 9 milliamps. And then we know that I2 is 4.5 milliamps. And what we don't know is we don't know what I3 is here. And that will all be equal to 0. Simplifying a little bit, we can add the 9 and 4.5 milliamps, and we get 13.5 milliamps. And plus I3 is equal to 0. We'll keep I3 on this side of the equation, and moving the 13.5 milliamps, what we'll do is we'll subtract it from both sides of the equation, and we'll end up with a negative 13.5 milliamps. So what that means is we know that it's negative 13.5 milliamps flowing out this way, and so reversing the arrow would also reverse the sign on it, meaning that this is 13.5 milliamps flowing into this node. And it makes intuitive sense. 13.5 milliamps flowing in, 9 milliamps flowing this way, and 4.5 milliamps flowing this way. Likewise, we'll have the same sort of thing going on down here, where 4.5 milliamps is flowing into this node, 9 milliamps is flowing into this node, and 13.5 milliamps will be going out of this node back into the battery. And again, because this is, we've got two arrows going in and one going out, we would actually mathematically write it with this arrow going back in, and this would once again give us the minus 13.5 milliamps. We can also simulate this 2 resistor circuit in Falstad simply by adding another resistor. In this case, we'll have to go ahead and change it to be 2K ohms. We'll go ahead and add another ammeter for that particular resistor to be able to see the current going through it, and then we'll replace this wire here also with an ammeter, which will give us the added resistance of the two. Now we just have to wire the two together. As you can see, the additional results that we calculated are available here. We have 4.5 milliamps going through the 2K ohm resistor, and then the total going through the circuit is 13.5 milliamps. Now we can also demonstrate it with the battery and an additional resistor. So in addition to the 1K resistor that I had in the last circuit, I've added a 2K ohm resistor here, just like our circuit diagrams we were playing with before had in them. I've gone ahead and brought another multimeter out, and I've hooked it up to measure the current going through the 2K ohm resistor. We already know what happens through the 1K ohm resistor, so that we can verify that. And then I've hooked the outputs of the two resistors, or the side towards ground of the two resistors together, and we have the same gap here to measure the current through that portion of the circuit. Nothing is flowing in the circuit yet because this is a gap, and it isn't completed. The circuit isn't completed through the multimeters until I hook this up. And so when I do hook it up and complete the circuit, we now see that we're getting the same 13.5. It's a little higher than that. As we've seen across here, the batteries have a little bit more than 9 volts in them, so it's a little bit above the 13.5, but we also see that through this particular resistor here, we have 4.7 milliamps of current flowing through it. Resistors are passive components, which means that their characteristics generally follow relatively simple mathematical equations, and they can't directly do things like increase the voltage in a circuit. To be able to add our voltages, we'll need to introduce an active component into our module, an op-amp. In the next video in this series, we'll look at the basic operation of an op-amp and how it can be configured to add multiple voltages together in a circuit. If you're interested in continuing to get this kind of content, please consider subscribing to my channel. Also, if you have any questions or things you'd like to see in the future, please leave a comment, and I love hearing about the DIY projects everyone out there is working on themselves. Finally, I'm also on Instagram at EuroRack DIY, so drop by there too.